Okay, so the Maclaurin series is just a special case of the Tyler series expansion where x is at some point, and we can express it mathematically like this, where we have the f of x is simply equal to the f of 0 plus f prime 0 times x. And then here comes the tricky part. So the first thing you just need to remember is just the f of 0, so very easy, and f prime of 0 x, and then plus we have f prime of 0 times x squared over 2 factorial. And then you just continue. So notice the pattern. If you have double prime, you add a 0. Sorry, that's supposed to be double prime. This is triple prime. X to the 3 over 3 factorial. So notice third derivative to the power of 3 factorial. So let's do it one more time. So f to the 4, so that's the fourth derivative, 0, so you guessed it, x to the 4 over 4 factorial. Now for this you can just write a very easy formula. So I'll plus it one more time. Now instead of writing 4, I'm just going to write to the power of n, so you guessed it, the nth derivative times x to the power of n over, yes, n factorial. So we can then write that as the sum as it's approaching infinity for f of n times x to the n over n factorial. So usually if you're an IB student, this is given to you, so that's pretty easy. If you're an A-level student, don't think you do this. However, good luck. Okay, so I'll do a couple of examples. Find the Maclaurin series for sine of x up to the 7th term. So I'll give you a format that you can follow. It's pretty easy. So let's just reread. Find the standard Maclaurin series for sine x up to the x to the 7. Okay, so what that question means in particular is that you have to do this process up until 7. So you see I stopped at 4, right? However, you're going to have to do it up until 7. Okay, so how does that look? Well, it looks something like this. It's very straightforward. Watch this up. So we have f of x is equal to sine x. So usually what I do, and you can follow the same structure, it's pretty easy. Just go 1, 2, 3, 4, 5, 6, and 7. That means the 7th derivative. So you're going to differentiate this function 7 times in a row. Now it's pretty simple for sine, cosine, and so forth. However, it becomes a little bit tricky when you get very complicated functions that you have to differentiate 7 times in a row. Okay, so what's the differential of sine? Very easy. Cosine, the differential of cosine, negative sine x. The differential of negative sine is negative cosine, and then the differential of negative cosine is negative sine, so that becomes sine x, and the process repeats. Cosine x, negative sine x, negative cosine x. Okay, there we got our 7 differentials. That's the first part. Whoops, that's the first part of our structure. Next, you want to set up a structure where you evaluate. Let's do it again. F of 0. So 1, 2, 3, 4, 5, 6, 7. And we want to evaluate these differentials at 0. And you should notice that if we look at our formula, we can always see, have a look, f to the 0, double f double prime to the 0, etc. So it's kind of important that we want to differentiate at 0. Now I'll just write the first 2, but you'll notice what I'm doing. So usually you can skip this part. However, for the video I'll just do it. So it's sine of 0. So sine of 0 is what? 0, right? Then we have cosine 0. Cosine 0 is 1. So this is the process I'm following. I'm just plugging a 0 into this x. That's it. So 0, 0, and I write the answer over here. So the answer will be here. Okay. So we said sine of 0 is 0. That's -1. Sine 0, 1. And you can just see the pattern repeats himself for sine and cosine. The pattern always repeats itself. And ex. However, when ex has a maybe like a e2x, then it's a bit different. Anyway, let's go back here. So that's going to be 0. And again, -1. All right. We got our 7 differentials. That's what we need, x to the power of 7. And now we just plug this into Maclaurin's expansion. So I'll just rewrite it here just to show you. So f of x is equal to f of 0 plus f prime x times x, f prime 0 times x plus f double prime 0 x squared over 2 factorial. And then we just continue doing this up until we want. So we want our expansion for sine of x. So let's plug in what we know. Well, f of 0 was 0, so we don't have to write anything, right? However, we can see there that this is an x, right? So f of 1 becomes x, right? Since f prime of 1 or f prime of 0 is 1, so that's just 1 times x plus we have f double prime x squared over 2 factorial. However, this is 0. So if I plug in a 0, that will just be 0 times x squared, which is 0 over 2 factorial is 0. By the way, if you didn't know, 2 factorial simply means 1 times 2. That's all it means. So 4 factorial will be 1 times 2 times 3. Now let's look at our next expansion. We know it's just going to be x cubed over 3. So we have a negative symbol here. That means our next equation, I'll just leave the positive symbol here for now. It's going to be -1 times x cubed over 3 factorial. 4, we skip because it's a 0 again. Here's a nice little tip. If you ever see a 0, you can just skip it. However, we need to write 5. So 5 is going to be plus 1 x5 over 5 factorial. We skip 6. And 7 is just going to be minus. It's going to be x to the 7 over 7 factorial. And there we go. So now, let me just quickly rewrite this. We can say, well, sine of x is equal to x. X minus x cubed over 3 factorial plus 5x5 over 5 factorial minus x7 over 7 factorial. And that is pretty much the standard form for Maclaurin series, especially when you look at sine x. We can quickly check this out. So have a look. If we look at the Maclaurin series for sine x, very, very easy. You see? It's the exact same thing I had. It's x minus x cubed plus, and then x7 over 7 factorial. So we know we're correct in that case. Yeah, again, if we look at this, we can just see they just evaluate f prime, 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 and you can just plug in the numbers. Very, very straightforward, right? Very straightforward. Okay, so there's the Maclaurin series for sine. So let me just clean the board. Okay, let's do the next one. Next one's a little bit more challenging. So now they ask us to find the Maclaurin series for f of x cosine. So what I like to do again, I mean, you don't have to do this. I just like to do it. 1, 2. Oh, we only need up until x4. Okay, nice. 3, 4, x, x, x. I mean, I don't really think you can mess up Maclaurin series, to be honest. The only real way you can mess it up is if you don't know how to differentiate, right? If you don't know how to differentiate, obviously this should not be the first video you're watching. So let's quickly see, how do we differentiate the trig function? Or maybe this is the video to watch. I'll just show you anyway. Okay, so look at this. So cosine 3x. Well, in this case, if we want to differentiate 3 cosine x, what I can do is I can sort of think of this as f of x, and I can think of this part as g of x. So what I can then do is say f prime of x times g prime of x. Okay, so I can differentiate 3x. The differential of 3x is 3. The differential of cosine 3x is negative 3 sine x. So I can just bring this 3 forward. And there we go. Okay, so let's write down what we know. I'm actually going to use blue. It looks way nicer. So we have negative 3 sine x. Negative 3 sine 3x. My apologies. Just erase this bad boy. Okay, so it was negative 3 sine 3x. And now I'm just going to do it again. But be careful, because sometimes teachers tell you, whenever you see a function like this, sometimes teachers tell you, you can just multiply this number forward. Just multiply it forward and then differentiate the sign. But that doesn't always work though. It only works when there's a single number. The same as ex. When people tell you to multiply it forward, don't do it. Learn that the top of the function is gx, so we differentiate the top of e. So for instance, look at this. So it could be e raised to the gx. So you just write this e gx times g prime x. Okay? Anyway, out of topic, but I just want to make this very, very important. Clear, because in a case like this, where you have 2x plus x squared, they might tell you, oh, just multiply the number forward. But that doesn't work, because you're going to have to multiply 2x times 2 forward in this case. Okay? Very, very important. But for now, since this is a single digit, we can just multiply forward. So that becomes negative 9 cosine. Man, why am I making mistakes? Say negative 9 cosine 3x. And then the differential of cosine is negative sine. So that becomes positive 27 sine 3x. Again, I'm just multiplying the 3 forward every time I differentiate, right? Because the differential of 3x is 3. And our final one will be 81 cosine 3x. Okay, step 2. We figured out our step 1. Our step 1 is differentiate 4 times. And again, why do I differentiate 4 times? Because they ask us in this particular case for Maclaurin series up until the 4th term. So whatever number you usually see there in the question, that's what you're going to differentiate up until. Okay? Nice thing to keep in mind. So again, let's write down 0, 1, 2, 3, 4, 0, 0, 0, 0. Okay. So we learned previously that the differential of sine is sine 0, 0. In this case, however, 3 times 0 is 0. So that's cosine 0, which is 1. In this case, we have 3 times 0 is 0. Sine times 0 is 0. So negative 3 times 0 is 0. So that's 0. Then we have negative 9 times 1. We already know cosine 3x 0 is 1. So that just becomes negative 9. This again is 0. And here we have 81. Okay. Well, now that we have that, we can just plug it into a Maclaurin series expansion. So what do we know? We know that f of x is equal to, I'm just going to keep writing it just so it sticks. F prime of 0 times x plus f double prime 0 times x squared over 2 factorial and so forth. In this particular case, we now have, so that's cosine 3x. In this particular case, we have f of 0. F of 0 is 1. So now I'm going to plug in a 1. However, f prime of 0 I don't have, so I'm just going to skip it. Plus, let's plug in our negative 9. So I'll just put in the negative from the start. Okay, so negative 9. That's going to be minus 9 squared over 2 factorial. Okay, 3 we skip, and then we go to 4. 4 is plus, so it's going to be plus 81x to the 4 over 4 factorial. And if our question states that we need the simplest answer, or answer in the simplest form, we can then just say 3x approximately 1 over x. This one cannot be simplified, but 2 factorial, as I mentioned earlier, is 1 times 2, so I guess we can write it 2 plus. This can be simplified though, because we know now that 4 factorial is equal to 1 times 2 times 3 times 4. 3 can go into 81 27 times, so that's 27x4 over, then we're left with 1 times 2 is 2 times 4 is 8. So this will be our final answer. All right, easy stuff. Okay, let's look at our final equation. Like I mentioned earlier, you can't really mess up this, right? I mean, I don't think it's that difficult. People claim it's difficult. However, I would argue that this is pretty straightforward. All you really have to do is just not mess up your differentials, and you're fine. That's literally it. And plug it into the equation. Okay. Anyway, so it's ln. Like for instance, this one, if you mess it up, it's understandable because this one's quite challenging. The previous ones were pretty easy. I mean, I would argue that the one before this was also pretty challenging, but it's okay. Anyway, let's go do our thing. F2. Okay, let's see what we can do here. Okay, the differential of ln, very, very easy. Okay, maybe not easy, but it's okay. Show you guys. Think about this part as, again, think about that as g of x. So it's going to be 1 over, we can think about g of x times the differential of g of x. Okay, that's how you solve ln equations. Sometimes people would tell you, hey, just put it over 1 over x, right? However, you should do this. Look, d over dx for ln x is equal to, I mean, we know it's 1 over x, sure. However, it's times 1, right? Because the differential of x is 1. So we get the differential of x, boom, boom. So we now know how to differentiate ln. So let's do that here. So we know it's 1 over 1 plus 4x, since 1 plus 4x can be thought of as g of x, times the differential of the inside. So the differential of the differential of a constant is 0. The differential of an x is 1. So it's just 4. It's very, very easy. Okay. Okay. I'm actually going to rewrite this. I'm going to rewrite this as 1 times 1 plus 4 following exponential rules to the power of -1. Now this becomes a lot easier to differentiate. Man. Okay, here we can use the chain rule. Have a look. Multiply forward times the differential of the inside. Okay, so if we multiply forward, that becomes -4, and I'm going to write the inside times the differential of the inside. The differential of the inside is 4 again. So we get -16, 1 plus 4x. Okay, you see, this one becomes a bit challenging now. Let me just get rid of this stuff on the side here. Okay, to the power of -2. Sorry, I forgot to subtract 1. Okay, let's do it again. Multiply forward. Oh, hell no. I need a calculator. Anyway, I'll quickly write it here. So it's going to be, it'll be 32. That's 32. Okay. Oopsie. Let's have a calculator here. So look, in this case, I'm just going to multiply forward times the differential of the inside. So it's going to be -2 times that. It's 32 times 4 is what?
128. So this differential will be 128, 1 plus 4x, sorry, 4x to the power of negative 3. The next one will be negative 3 multiplies forward. That's negative 3 times 128. That's 364 times 4 is 1536. That's minus 1536. 1 plus 4x to the power of 4. Okay, there's our first one's finished. So you see what I mean? I said the only way you can really mess this up is if you don't know differentials. Like in this case, you need to know that, well, you can rewrite this as a negative exponent, then use the power rule. But then you also need to know how the chain rule works. You see? So it's a bit tricky, but yeah. So f of 2, so f of 3, so f of 4. Okay, let's evaluate these guys. Let's see. I'm gonna change colors because this one's a bit tricky, so I'll make it red. If we plug in a 0 here, that's 0. So ln1 is equal to 0, right? So that's 0. The next one is, what's that? That's going to be 0, so that's 1. So over 1, so that's 4. I guess we can just take the coefficients. It's going to work. However, I don't feel nice about the second one though. I think there's something wrong here. Let me check quick. So oh man, it's 32, right? Did I mess this up? Hell no. No, it's negative 16. Okay, look. Multiply forward. Negative 4 times 4 is negative 16. Okay, then we have 128, and then we have negative 1536. All right. Now that we got that, we can plug it into the Maclaurin series expansion. Again, I'll just write it here. So times x plus f double prime 0 x2 over 2. And this is all you need. From here, you just take the derivatives and put all of those equal and so forth. Okay. So what did we need? What was our f of x? So f of x was ln 1 plus 4. So we can then say ln 1 plus 4x is equal to f of 0 was 0. F prime of, so that was 4x. So we get 4x, and they only want up until the fourth term. So that's okay. Okay, so use your series to find an approximate for ln 1.04. Okay, so I guess we can do that in a bit. So then we have plus f double prime 0 x squared. So f double prime with 0 was negative 16. So negative 16 x squared over 2 factorial plus. You see, you just take these numbers and plug it into the Maclaurin series. Very, very simple. 128 x3 over 3 factorial plus. It was minus. Minus 1536 x4 over 4 factorial. The second part of the question is use this series to find an approximate for ln 1.04. Okay, so in that case we first need to solve what x needs to be to go into the Maclaurin series. So we know that 1 plus 4x should be equal to ln 1.04. So there's two ways we can solve this. However, we can then see in this particular case that x needs to be 4 times 0.0. What's that? 0.01, right? Gives you 1.04. 1.04. Let me just double check that quick. Because we have 4 times 1.01. Boom. 0.04 plus 1 is 1.04. So we know that x is then 0.01. Okay. Well, now that we know what x should be, we can then plug that into the Maclaurin series. For that, I'm going to need a better calculator though. So let's go to Desmoses. Okay. So it was 4, 0.01 plus. I can't mess up these symbols. Oh, it's minus. Sorry. Minus. Is there any way I can bring it here? Okay. Minus 16 to factorial. I'll just copy and paste this one. Makes it a bit easier. And that was squared plus 128 3 factorial. Now you can simplify these ones before you start, of course. I'll show you in a minute what I mean. Minus 1536 over 4 factorial to the 4th power. Okay, so there's our answer. However, the question was, use the series to find the approximate of ln 1.04 up until the 6th decimal place. So in that case, we can, after substituting this in, so what you should do is, oh man, I guess we can write it. So ln 1.04 is approximately, so now you can write 0.01 plus negative 16. What I meant earlier was you can simplify this, because negative 16 over 2 factorial just simply means negative 16 over 2. So that's negative 8. If you really want to. I mean, I don't think anyone really cares too much if you simplify or not. That's supposed to be a negative, sorry. Plus 128, 0.01 raised to the 3rd over 3 factorial minus 1536, 0.01 raised to the 4th over 4 factorial. So we get an approximate. If we go to the 6th decimal place, it was 039220. Wait, so 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6. Okay, so we leave it there. Maybe we can make it 1. So 0, 39, 22, 1. So 0.39, 22, 1. So there's your final answer. So you leave it in this answer, and you're all good to go. Okay. Great stuff, great stuff. Very easy. Now get out of here for real, man. Get out of here, man. Shh. Get out of here, man.